It's my pleasure to begin this day with a keynote speech by Vivek Sarkar, who is a I better not butcher this. He's a professor and chair of computer science at the Rice University. He's the ED Butcher. I had these initials in my head, ED Butcher Chair in Engineering. And I knew Vivek from many years ago, mostly from his time as IBM research, where he was in charge there might be a formal position, but he was involved in charge of the productivity aspects of the HPCS, the productivity, the DARPA project aimed at improving productivity in parallel programming. He was involved in development of X10. Probably prior to that, the JIX runtime system, and his expertise in compilers is well known. He graduated from IIT Kanpur with his bachelor's, master's from Wisconsin, then PhD from Stanford, and so on and so on. There are many other things that I could mention. He's a fellow of the ACM, and he's now leading this OCR effort that we'll probably hear more about. That's an open community runtime effort. So without further ado, Vivek.
Okay, thanks, Sanjay. Thank you. So I remember when I first joined IBM, Sanjay invited me to visit, and maybe 1989 or 1990. Was your group called PPL at that time too? Oh, wow. And at that time, Sanjay's mind had many things. It had the charm-related stuff, but he also would talk about functional programming and logic programming, and so we had lots of good discussions that date back a long time. Lots of good arguments too. So acknowledgements to the team. There's the work that I'm going to present is really obviously contributions to the team. It's a good group that works together in terms of research scientists, postdocs, and graduate students, and of course to us, acknowledgements to our sponsors. So just to set the stage, and everyone here knows this, for about 7 or 8 years now, we've had a good sense at a high level of what's coming in terms of extreme scale systems. So I had the opportunity to lead this DARPA exascale software study in 2008, 2009. And very early on, we decided to refer to these challenges as extreme scale rather than exascale because we saw them occurring across the board. The changes were, the fact that your building blocks, the chips are going to be, and have already become massively multi-core, homogeneous, heterogeneous, performance driven by parallelism, constrained by energy. It's almost, and we've heard talks related to that, like a bin packing problem almost, and resilience issues. So these were the key challenges, and that's really guided our research and many of the research of many other people in the community. Today's talk, I decided to focus in the time that I have on hybrid programming because that comes up as a pain point. You hear of people really struggling with combining message passing and task parallelism, with combining CPU parallelism and GPU parallelism. So the word hybrid is used for all of those. So I wanted some interesting images because I don't normally put interesting graphics. I looked up Wikipedia and found some interesting hybrids that apparently were actually bred. There's a zebra and a donkey, a lion and a tiger, a jaguar and a lion. So the thing is, you can do cool stuff, you can build, but I think our goal is not to build one-offs. We want to find solutions to hybrid programming that would really lead to a more sustainable ecosystem rather than a one-off demonstration. I think what is considered to be hybrid depends on where you start. If you start with a very limited model, let's say that is bulk synchronous SPMD, notion of fixed number of ranks, then many things turn out to be could be viewed as hybridization, just even asynchronous data movement or task parallelism within the rank or adding accelerators or trying to do migration. These all appear to be extensions that are somewhat different from your starting point, and then you have to work on kind of banging heads together to make it all work. On the other hand, if you try to go for something that's hybrid by design, which I think is also the goal of the Charm++ project, the idea is that you look for some unifying principles. so that once you have these unifying principles, then the combination of features just work out naturally within the same framework, and you have semantic guarantees that come about from the combination. So some of the same things earlier can actually become easier, and I'll show examples when you have a unified model. I didn't find a good graphic for the positive hybrid by design. There must be one, so the best I could come up with was like an early Prius thing. But that's an example of something that was hybrid by design rather than hybridization, which might be, okay, go put a battery in your back seat or something. Okay, a related thing that many of us in the community have discussed is that who's our audience? Well, the developer community is very large, and in many working groups, we've had this inverted pyramid, sometimes with 2 or 3 levels. So there are domain experts at the top who really just want to solve problems. And they don't want to care about parallelism. They have enough challenges as it is. There are concurrency experts at the bottom that use low-level parallel programming models and actually relish in all the fine-grained details. You can have entire PhD dissertations on non-blocking queues and things like that. And in any ecosystem, a critical role is played by the software engineers that bridge the gap. This is exactly what happened with object-oriented programming too, where the bottom of the pyramid might have been, the compiler or the implementers of Smalltalk and C++, and the software engineers are the ones who built a lot of the frameworks and enabled a lot of applications. So we've been guided by that as well, and our goal is to try to find unifying principles, but we focus much more on the upper levels. And this is not drawn to scale, at least not to linear scale. One could argue that's at least log scale in height in terms of the numbers of domain experts, software engineers, and concurrency experts. And some of our experience has been, in this execution model that I'll share with you in terms of the primitives. Those can be directly available at this mid-level, and we already have them available in C, C++, Java, Scala. But an area that we really want to explore more is higher-level frameworks on top of these primitives. And so far, our experience has been in our collaboration with Kathleen Nobe and others at Intel on the CNC project, where we've created environments of domain experts where they could write steps in MATLAB or Python and so on. Okay, so here's the sort of the context for our group's research. We focus really on the programming models, compilers, and runtimes. To a large extent, the application work and the hardware work are like boundary conditions for our research. It's really been great to see the work in PPL with very, very active involvement with applications. We don't have that level of involvement, but we have some. Sitting in Houston, we've now begun interacting with local oil and gas companies and also with the medical center. And so our engagements tend to be folks more on the mid-level parallelism stage, not the very high end of supercomputing. But obviously, we're interested there too in our work with DOE. So there are these primitives that I'll talk about, and our goal is to bridge the gap using these 2 levels of programming models. And we've also experimented with a wide range of hardware, and in our effort to try to really push the boundaries of what could be done with hybrid approaches, we want to look for things as diverse and heterogeneous as possible. One that I'll show you results for is where we were able to have FPGA, GPU, and CPU cores all in the same platform addressed by a unified programming model and runtime. Okay, so what are the elements? And this has been gained over experience at the highest level, and this is really our goal, is to come up with this unified model that can map onto this wide range of extreme scale platforms, not only what I showed you earlier, but what we expect in the future. So we believe that asynchrony is key, and and that's something that Charm++ I know believes in also. So have primitives in the execution model for creating asynchrony tasks, terminating, waiting for sets of tasks, and data transfers. A key belief for us in this unification is that data transfers and computation should really be treated on par, and you'll see examples of that. Then locality control, which really is generally computation and data distribution. It can apply to clusters, but it can apply to even within a node and cores within a chip. And a global namespace plays a key role over here to allow for the hierarchies of memories, like we heard from Bob Wisniewski yesterday, with non-volatile, volatile memory, and so on. And finally, these tasks often need to interact with each other beyond the termination. If the tasks are small, very often the interaction is that you just wait for them to complete, and that triggers a new event or some new ability, but very often there's a need to do other kinds of operations. And there we've split it into two parts, a mutual exclusion and a collective and point-to-point. So I won't have time to talk about all the primitives, but in general, this is how we frame it. And as an example, and this is what I use in my class, if you take something like a CUDA kernel invocation, that seems somewhat different, and adding it to your model is hybridization. You have to do this triple angle bracket thing. In our model, well, a CUDA kernel invocation is just an asynchronous task invocation at some other place, and the body of the kernel is two levels of parallel loops, where the inner parallel loop is phased, meaning that it can have barrier-like phases. And of course, CUDA has specific notations for all of this, like sync threads to the barriers and block ID and thread ID, but that's really the abstraction. And then, all the properties I'll show you will follow for this as well. So here are some of the properties and why we see benefits in taking this approach. Sometimes people get into religious wars saying that you can express any algorithm or any application in any programming model, and that's kind of like the Turing machine tarpit kind of thing. And I believe that is possible. You can give people threads and locks, and they can do everything. But the question is, what semantic guarantees do you have? Just like type systems give you a rich set of semantic guarantees, I think these primitives also do that. So one is the primitives, like for instance, using something like finish or Chapel's sync or even Silk's spawn sync and other primitives guarantee deadlock freedom for a large subset of operations. In fact, we have only very specific operations that are really advanced features that could potentially cause a deadlock, such as explicit wait in phasers and explicit wait in async. Data race freedom is much, much harder to guarantee, but there are certain cases like values in futures, values in accumulators. There's some work we did on read-write permission regions, there's isolation actors. These all guarantee data race freedom. Determinacy, and this is something I've had the opportunity to discuss with Jack Dennis at great length. We wrote a paper also with our definition of determinacy, which includes both functional determinism and structural. Structural means for the same input, you'll always get the same computation graph, and not just the same output. And it turns out data race freedom implies this powerful determinacy property for a large set of constructs, but excluding the mutual exclusion. So it turns out isolated actors are very elegant ways of getting data race freedom by default, but those constructs actually should be used if you intend to have non-deterministic computations. And there are other things like accumulators and other properties, other constructs that can give you determinism and data race freedom without getting into isolated actors. And then the point is, we don't want to just come up with the lambda calculus of these primitives. We want to make sure these primitives are capable of being implemented efficiently. And our work and a lot of other related work has shown that these primitives can indeed be implemented efficiently and also integrated with each other. So here's another way of looking at what I just said. That is, if you can classify programs as deadlock-free, data race-free, determinate, class where data race freedom implies determinacy, and serializable, meaning where you have a very simple transformation procedure to convert your parallel program to a sequential program with one possible semantics for your parallel program, or equivalent semantics, let me say, but one possible execution. And so, for instance, the Silk folks had advocated this for a long time with the elision property, saying you remove the spawn and sync, and you can debug a sequential program. So we can see that, if we use these async finish future constructs that are task termination, creation and termination, you're in the serializable set. Adding barriers actually loses the serializability. So as you add more constructs, you get more generality, but you lose some semantic guarantees. So the reason is, if you can imagine a for loop with a million iterations, phase 0, barrier, phase 1, and you say, okay, let me throw away the parallel loop and the barrier and execute it sequentially, that won't be a correct execution, because iteration 0 will do phase 0, phase 1, iteration 1 will do phase 0, phase 1, and so on. You have to transform it in a different way by distributing the loops and so on to get an equivalent sequential program. Yes? Yeah? Oh, sorry, the plus is, put parens around DRF implies det is one term. So it's not DLF plus DRF implies determinacy. It's you get deadlock freedom and the property that Datarace freedom implies determinacy. So I should put parentheses. Okay, good. And then if you then add this data-driven tasks, event-driven tasks, which give you more generality, you use the deadlock freedom because you can create tasks that wait for events that never show up. And you can argue whether that's technically deadlock, but that's a form of progress, the lack of progress, that's like deadlock. And then, of course, if you restrict shared addresses, you get data race freedom, and they don't all perfectly nest. In particular, you can see this is data race freedom, but determinism slices through all of them. You could have programs with data races that are deterministic, depending on your memory model. Okay, the other thing that I've really enjoyed doing after moving to Rice is develop this undergraduate class, which is now taught at the sophomore level. It's taken by CS majors and non-CS majors. And the approach is really to introduce them to the primitives. Of course, if I really want to do something for the uppermost part of the pyramid, we could just teach them something like MATLAB or LabVIEW and let the tool chain take care of the parallelism. Here they're learning about stuff under the hood a bit, where simple things are simple, but complex things are also possible, and they learn about all these constructs. Now, for these people, they haven't even learned, they haven't taken computer architecture, they haven't taken operating systems, they don't, in our curriculum, at least at this stage, they haven't learned to program in C. So this class is taught using, a Habanero extension to Java, but we could imagine this material being taught with something like a Habanero C++ as well. And I've now begun creating short videos, like 5 to 7 minutes for the different principles. Okay, so now, having said all that background, let me just give you a flavor of some of the primitives and try to get at the interesting hybridizations, because that's the focus of this talk. So task creation and termination, there's different kinds of notations. I'm using the one that came from the Extend project, where async creates a task. So it's just like, and then finish has a scope, and at the end of the finish, you wait for only those tasks to complete. So it's a little different from join all or from silk sync, which just joins for everything in the past that has been created. You can nest finish and async as deeply as you like, and the scope is always very clear, because every async has a unique dynamic immediately enclosing finish, and that's the one that waits for it to complete. Now, one thing, and this will come up later when we start looking at communication, this async could be a computation or a communication. So if you send out a whole bunch of non-blocking messages, and we have an example of that when we integrated Habanero C with MPI, the finish will wait for all the non-blocking messages to complete before going past it. Getting back to the properties, even though finish is a synchronization, it's a restricted kind of synchronization, so you cannot create a deadlock cycle with it. And the way to think about it is, if you think of the task creation tree, finish is always, you're always waiting, always have an ancestor waiting for a descendant, so you cannot create a cycle. So here's an example of, and I'll show you examples with both Java and C as the talk proceeds. So this is an example that I teach in my class of this parallel spanning tree, not minimum spanning tree. They do a parallel minimum spanning tree later also with Baruch's algorithm and so on. But this is very simple. Just do a depth-first traversal, and when you're done, the input is every vertex has a list of undirected graph, list of neighbors, and when you're done, every vertex has a parent. That should be a spanning tree. If you do the elision and just ignore the red stuff, you have pretty much a sequential computation where you call compute on root, visit the neighbors, you try to become the parent, try to make each neighbor the child in the spanning tree. If you fail, then you just go to the next neighbor. If you succeed, then you call compute on child, and so on. Now, for the parallel version, the main insight is that when you're visiting all the neighbors, you could do that in parallel. So we wrap this in async. By the way, this is the new lambda notation in Java 8, in case you haven't seen it. And I think this makes things also more synergistic with C++, which now has lambdas as well. You put a finish, and this shows how it can be interprocedural. The finish is right at the outermost level. You just want to wait for all the asyncs to complete. In this computation, you don't need to wait level by level. But in a model like Silk, or actually even OpenMP, you require parents need to wait for children. So the waiting would go level by level up rather than just once at the root. And one of the tricky parts over here is, and this is a non-deterministic algorithm, because for the same input graph, you could get different spanning trees as output. The tricky part is coordinating this access where there's a shared field. Two vertices could attempt to be the parent of the same child, and one of them has to succeed. So isolated, and we'll talk about object-based isolation briefly later, where this is with respect to this object. And a clever compiler can actually recognize that this matches a compare and set instruction, and you can implement the semantics that way. So this gives you a feeling of how things start composing. There's a notion of escaping asyncs, which means the method can return before the async completes. If you don't want that, just put the finish around the method body. Yeah. Oh, this is this child or try labeling this. So what you're saying is you pick a neighbor, you want to make it your child in the spanning tree, you call try labeling on the child, and this is n is the node that's attempting to be the parent of that child. So once you call try labeling, this is the child over here, and n is the node that attempts. Yeah, we can talk about. And the business about final is only because Java 8 lambdas require these any locals that are outside the scope to be effectively final. You don't always have to have a final declaration, but that's sufficient. Okay, so now let's expand the aperture a bit and talk about event-driven or data-driven tasks. Yes? Yes. So the thing is, how you prove it, so that I think is challenging. So this intuition over here is that all shared accesses occur in isolated. Well, you could have a type system, and we've done this. We have a permission-based type system, for example. So you could do that. Right? No, what I said was, yeah, I said, well, two things. One is data race freedom implies determinacy, and then how do you guarantee data race freedom? If you restrict accesses to futures, accumulators, isolated actors, all your shared accesses. Now, how you restrict it depends on a combination of the programmer, the programming model, type system, and so on. Well, it depends on the memory model. So, yes. So now let's extend our notion of tasks towards these event-driven or data-driven tasks, which really actually capture a lot of the hybrid capabilities that we want, because when you offload a GPU kernel, you want to be notified when it's terminated. When you initiate a data transfer, you want to be notified when it's terminated. So the model is, and now I'm switching to C-like syntax, we have it in both, where you have an async, but you have preconditions to say that this task can only start executing when some events, or what we call data-driven futures, for historical reasons, become available. And we really want determinism with this construct. So we require that these data-driven futures are single assignment, or you can think of it that, single assignment events, which can be triggered by any task by doing a put in this data-driven future. And then within the body of the await, within the statement, you can do gets in the data-driven future, but no blocking is needed at that point because you would have already done an await. And in fact, in our Java-based implementation right now, we have an exception if you attempt to call get in a task without having done an await on it. Okay, so what can we do with this? So here's an example of a Smith-Waterman tiled version, simple dynamic programming, where what you want to do is, rather than get into explicit wavefronts and parallel loops, just specify the dependencies. So the way you would specify the dependencies is you break it up into tiles. I'm not getting into the computation in each tile, that's in compute. And each tile is an async await that waits for the DDFs corresponding to the three predecessors according to dependencies, above, left, you left. And then you do a put on your DDF. One interesting thing, and this comes with the power of the model, is you could run these loops backwards also, and the semantics would be exactly the same. Your performance may not necessarily be the same, but the semantics would be the same. You're creating a bunch of tasks with dependencies, and this is a question I often give my students in a quiz or midterm, is, will the thing terminate if, for instance, I went from H minus 1 to 0, J went from W minus 1 to 0, and that's fine. You're just creating tasks backwards, but each has their dependence. When the first task executes, it then releases successively all the other tasks. So this all fits under category 1, just to say this is where we create asynchronous tasks and coordinate them. So these are primitives. You saw finish, you saw async await, and they have different places in that Venn diagram. The second category of primitives that we have relate to locality control. And primarily, I mean, when this is still a subject of ongoing research, but right now we're primarily thinking of these as tuning hints. That is, they are separation of concerns. The locality annotations don't change the meaning of the program, but could have a huge impact on the performance. And one of the abstractions that we use to guide this is this notion of a hierarchical place tree, which is really an abstraction of that's convenient for both the hardware and the application. And in fact, you could explore multiple HPT configurations of the same hardware and application, and certainly different applications might want to view the hierarchy in different ways. So let me give you a little more of an operational view as to what it does. So there's an at clause for an async that is trying to give some affinity. Now, in the hierarchical place tree abstraction, we are abstracting the machine as a tree, and the at is logically saying put it in a queue, though it's not a first in, first out queue, like a set of tasks to be executed at some level. And at least for now, the policy that we have is that a worker only picks up tasks from its ancestor places. Now, with that policy, the way the locality control comes about is if you put a task somewhat higher in the tree, like at the root, it can be executed anywhere, so it's better suited for load balance, but it doesn't really have any affinity. Whereas if you put a task, let's say, in place 2, it can only be executed by these 2 workers, even if those other workers happen to be idle. Now, people in my group are exploring variations of this, maybe where an adaptive runtime might percolate this up, and even this hint can come from the compiler. We have some collaborations with Reservoir Labs where they're looking at compiler generation of these hints, and of course could come from the programmer. So this is just some work from a thesis that was recently completed by Sanjay Chatterjee. And one of the things we find is that the impact of these annotations is a little harder to measure on today's hardware, but our belief is going to become more and more important in the future. And certainly we see bigger impacts when we count cache misses compared to just measuring time. So this is a tile Cholesky, and something happened with the PowerPoint going from Mac to Windows, I guess. But this is a tile Cholesky example where the baseline is the blue line and the red line is hierarchical place tree. Same computation, but just an affinity on where things should coexist. With a large enough tile size, like 125, it's really compute bound but as you get to smaller tiles, and we believe this will be a trend in the future as the numbers of cores increase, we could see a bigger impact of locality, and that makes sense when you have smaller tiles, that execute for shorter amounts of time. The opportunities for shared cache reuse increase. Just to give you a feeling how this could be done, we've also experimented with some mini apps, including Lulesh. In Habanero C, what you can do is the place is just, it's a notion, what you can get from a place is you can get, anytime a task executes, it can capture its own place, maybe store it. So here we are assuming that the user has some function that returns a place where a tile of iterations like I out to IN may have been executed in an earlier call. We say we want to bind it at that same place, which may not be the leaf, it may be some mid-level. And this reuse can take place across loops and different functions. And so even though there are compilers that do locality optimizations, when you have large applications with loops spread across many procedures, these kind of affinity hints can help. And again, for Lulesh on today's machines, we see a little bit of a benefit. This was again on the 12-core machine with using places. We see more significant improvements in this case in the L3 cache misses. It's 1.5 times, well, in the unoptimized one has 1.5 times the number of cache misses as the optimized one. For some reason for this setup, we actually saw an increase in TLB misses. So that's the kind of thing that we're in the process of figuring out. If anyone is really interested in these memory hierarchy details, let's talk later. Now, once you've got this hierarchies, it's just another step to think about heterogeneity, where you can think of some places as heterogeneous. And like I showed earlier for the CUDA kernel, the async at notion can be extended for heterogeneity, and you need the compiler support to do the copy in, copy out of appropriate data, the explicit data transfer. I don't have time to get into the details of the runtime, but there are these proxy agent workers where we use CPU cores as workers that communicate with the GPU devices, and we can do work stealing across GPUs as well. So looking at some example, this is in our collaboration with UCLA and others in our NSF Expedition Center for Domain-Specific Computing. I'm just going to look at three stages in the imaging pipelining: denoising, registration, segmentation. And this is just and actually this work was done by taking CNC and mapping it onto our primitives. So a CNC program has a graphical specification. This is a textual representation of the graph. The student leading this work added some annotations to say what, again, these are tuning annotations for each step. There could be multiple versions available. Denoising has CPU and GPU versions available. Registration has GPU, FPGA. And segmentation only has GPU. The numbers are not really significant other than there's a preference to run the step on the device with the highest number. And here are the dependencies, and here's a schematic of our runtime where these tasks are created. Essentially, async await captures the CNC model, because CNC is all about creating tasks and making the dependencies explicit. And you know, we have our runtime has queues for and allows for cross-device stealing when there are multiple versions available of kernels. And so this was evaluated on one of the test beds that I mentioned, where we took a Conway node, which has a very nice integration with FPGA and CPU compared to just sticking a Xilinx card, because they share a memory controller. And then, but we added a GPU to it. And one thing we observed was the static schedule, meaning just obey the highest number for each step. And this is a very simple dependent structure, actually, not even like Cholesky, where you have 10 independent images, and each image has a pipeline dependency. So from denoising 0, registration 0, segmentation 0, denoise. So if you do that, then the schedule ends up looking something like this. I'll show you some more details in the next slide, and ends in something like close to 190 seconds. If you allow for that dynamic inter-device work stealing, we're able to complete sooner. And the details are over here, where now here we get into a bit of the details of our runtime, where the fact that we use designate a core to be a CPU core to be the proxy for the heterogeneous device. So if we just run that workload on 4 CPU cores, we get a completion time for those 10 images of 2200 seconds. What I'm showing on the right-hand side is a very crude estimate of energy, which was just obtained by taking the active time for the device, multiplying it by the power. We are now using things like RAPL and all with the collaborations with Intel. But there's some estimate in kilojoules for doing all that work, close to 70 kilojoules. At the GPU, significant time reduction and energy reduction. And many people believe that the first path to having lower energy is get the job done faster, race to halt. Then hybrid CPU and GPU, you get a slight reduction, not a lot. But we're using 3 CPU cores because 1 CPU core is tied to communicating with GPU. We don't expect this to be an issue in the future as we go to tens and hundreds of cores. Then if you use the dynamic schedule, we have 129 seconds. The static one, as I mentioned earlier, has a longer time. However, the estimated energy is lower because the static schedule was, the GPU was the highest, had the highest power consumption of all these devices, and FPGA was particularly energy efficient. And what the dynamic schedule did was ended up taking some of the FPGA tasks and executing them on the GPU as well. Yes? So the representation is, and I don't have slides on that, but so the way CNC works, and I assume you've heard CNC talks before from Kath, is that you specify your program as a graph that looks like this. And you have a tool chain, a little bit like your configure, or whatever the CI file is called in Charm++. From that graph, you generate a whole bunch of header files and so on. And then the user provides the essentially sequential code for each of these steps. Now, the question is, how do you get the FPGA and GPU versions? So in this collaboration with UCLA, Jason Kong's group has done a lot of work on synthesizing FPGA code from C, so we use that over here. And we have also done work on generating OpenCL from Habanero C. So that's how it would work out. There are some optimizations, yeah, and there's some tuning, yeah. But this, at least in terms of the coordination, that's, and so there's performance tuning you can do to give hints as to what data should be stored in. It's CNC or async await, depending on your perspective. Yeah, they really have identical semantics. So if you like the coordination language approach, you can use CNC. If that messes up your build system and your make file, you can use async await. Now let's go to the other level of the hybrid pain point that people usually talk about is, the classic, how do you combine OpenMP and MPI and so on. So in our model, we've done this work recently, and it was mentioned yesterday also in one of the talks, is in integrating Habanero C with MPI. So what we'd like to do is take the primitives and then look at MPI operations, like especially the non-blocking ones, MPI send, MPI receives, just like asyncs. So when we have a finish over here, we've launched some computation S1, we've initiated some communications. We could have one of the communications could, have this request, standard MPI request, and we can use an MPI request as also one of the preconditions in async await. So what this means is that whenever the receive is completed, it'll trigger the execution of S2. We don't need to do our own polling or MPI wait and so on. That's all taken care of by the runtime. And S3 is something that can run in parallel with all of this. And finish says, let's just wait for that whole caboodle to complete and then move on to the next thing. How it's actually implemented in the runtime to help with the unification is we have, first of all, for the malleability, we have the computation workers and classical work stealing, so the number of workers can grow and shrink as much as you like. And we're doing a lot of some recent work on that related to energy optimization. And then we have a communication worker where one communication worker can serve some number of computation workers. And this is similar to the communication engine idea that you heard about yesterday. And so the communication worker is responsible for interacting. And in fact, when we run with MPI, MPI really thinks that we are running an MPI thread single mode. And it only knows about the communication worker because that's the only thread or performing MPI calls, whereas actually we have all this other task parallelism going on that MPI is oblivious to. And the number of communication workers and computation workers is also a tuning parameter depending on the network bandwidth, what degree of parallelism you want in terms of injecting communications into the network and so on. And so one of the benchmarks that we tested in this synthetic kernel, unbalanced research, just because that's irregular, there's a standard MPI implementation that does dynamic work stealing where the programmer quite tediously, use MPI messaging to steal work across MPI processes. And that's our baseline. And then what we did is, we obtained these results on the Jaguar computer before it was replaced. So we went up to 1,024 nodes and up to 16 cores per node. By the way, the PDF file should not, or if it does have these quotes and stuff, I'll replace it. And the ratio shows the ratio of the MPI reference divided by the HCMPI version. For these results in the HCMPI version, we only created one communication worker per node. So basically, there were 1,024 MPI processes for HCMPI, whereas there were 16,000 MPI processes for MPI. And you can see, and we also have, because we're using one core as a communication worker, you can see that we had, in the two-core case, I should have put a label of 1.0 over here. The performance of HCMPI was below MPI, but once you have enough cores, it more than dwarfs. In fact, there was some scalability issue that MPI was running into at 16,000 processes for this code. Okay, so I'm running short on time. I know we started a few minutes late, but I'm going to start wrapping up. It turns out that whole async await idea can also be directly executed in the distributed context. And in this sense, it's a little in the spirit of Charm++, in the sense that these data-driven futures can be just distributed across places and nodes. And the put-get, the runtime takes care of communication for put-get. If the producer and consumer on the same node, it's more efficient. If they're on different nodes, the runtime generates the communication. The difference, one key difference with Charm++, I'd say, is that these are very much part of the deterministic parallel constructs, the async await, whereas Charm++, and we get good results here in terms of scaling this on a more modest cluster, 96 nodes, 12 cores per node, and you can see improved performance both with increased number of cores and increased number of nodes. And with Charm++, that's more like what we view as our integration with the actor model. In the interest of time, I'm going to completely skip over the isolated stuff, which actually interacts a lot with transactional memory research, and we've done some work on comparing it, for example, with the Galois system, and instead of having a special runtime, just like Galois does, just use this unified runtime with isolated. So I think, being at Illinois, all of you must have also heard about actors. There's so many parallel programming models being worked on at Illinois. And one of the things we did was similar to HCMPI. We worked on integrating task parallelism with actors. Actors are a very elegant model, and Charm++ has these properties and others as well, where each char or actor executes its code sequentially. You don't have to worry about data races on the local state. But we wanted to add parallelism, and I don't have time to get into all the details, except to show you a simple example where we can do a finish, and this is again from my class, where you can start a bunch of actors and do a finish and wait for them to terminate, and that way you get a convenient hybridization, whereas sometimes termination can be very tricky in the actor model. Also, you have to have semantics for ordering of messages. In our case, we require that the order of messages between the same sender actor and same receiver be preserved. Everything else, there's no constraint on the ordering. I'll skip this. They're also, you can think of these as asynchronous collectives, but the accumulator model, you can associate accumulators with the finish construct, where tasks can contribute values to accumulator, and at the end of the finish, you do a get, and you get the final value of the accumulator. And since finishes can be nested, these collectives can also be made hierarchical. So the role of the runtime system in all of this, I've really been trying to motivate some primitives, not really taking a stand on a particular programming model. I think different programming models can map onto these primitives in different ways. But I think the runtime actually has to play a key role in realizing these primitives and programming models. And you know, a robust runtime can then bring about this composability, like I've been showing you, of course, improve performance, enable new programming models, also simplify the interfaces for system software, so it's kind of playing a mediating role. So this is where, so runtime can mean many things to many people. So for what I'm going to talk about right now, for the last couple of minutes, is really the bridge between the programming system, language, compiler, and what I'd call system software. Now, many people would call some of these part of runtime. But I think with the extreme scale systems, there's a need that many people working on software stacks have found, and I think there's a commonality coming on for this bridging. In the old days, you would let an MPI process make system calls directly, but that makes things brittle for a lot of the adaptation we want to do, or a lot of the malleability. So having this adapter actually, I think, is very key as we go in the future. And then both Bob and Sanjay referred to this open community runtime effort. That's something that a group of people working in the Extract project are discussing very much at an early stage. And the idea is to find components where where we can that can be made available as an open source testbed, so as to reduce duplication of infrastructure effort, but allowing different research groups to pursue their own research agendas. And so this is at a lower level than a programming model level. So something like async await would be mapped onto something like OCR EDT create with a whole parameter list related to dependencies, affinity, and all of that. And so the vision is, and Bob had a slide related to this, you have an open community runtime framework, and it can be, maybe some people, more experts will program at those APIs, but otherwise you have higher level programming systems that map onto it, and we already have some examples. Definitely would like to explore, and we started some discussion with Sanjay about this on using OCR or using parts of Charm++ in OCR and getting more synergies there. There's also a foundation that's been created. The idea, if it succeeds, is to be, we have a narrower community in parallel computing, so create sort of the equivalent of Eclipse for this, for our community, and this is just starting out. So to conclude, I really think that, you need a holistic redesign of the software stack to address these challenges, and you need execution models and integrate these hybrid dimensions of parallelism and heterogeneity. So I've tried to give another number of examples where constructs can be composed and interoperate with each other in beneficial ways. And I think the runtime actually is key to making all this work, because we can create all kinds of models that we like. And OCR is one starting point for strawman community effort. Certainly, I would welcome talking to you guys during the break and the workshop as to what you see as the pros and cons of an OCR-like effort. We had a pretty active discussion of that at dinner yesterday too. So with that, I'll stop and welcome questions. Okay. Yep. Yes. Question, Brian.
That's by value. So you actually have to make a copy of the object as it goes in.
So there is a global, so the question is, well, I think you may have got it, whether async await has call by value semantics. There are parameters that can be passed, and that's the convenience. And but there are the body of the async. For example, it could do a get on one of those objects in the global namespace. And that's still, so they can be okay, well, that's not a good example, because there we would have done the communication before async await. Depending on what you put it in the, let's see, what?
So my thinking is, say I have a big iteration space. I'm going to break it up into tasks. Right?
Yes.
And But I'm doing the updates in place. So
Right.
I can actually put the big chunk of data in because
Yes.
I want the update to go back into that big array.
Yes.
And someone else has to know that you're done doing your part of the stencil. I can start working on my stencil.
Right.
So,
the way we would do it is like the tile Smith-Waterman example. We would create a tile of these data-driven futures, and the await basically waits for the tiles.
it waits for the tile to finish, but not necessarily the data that's behind it. So
well, it would, if it actually reads the data, then and if it needs to perform a get, so you can use the await in two ways. If you're doing some imperative programming under the covers on your own, you can just use the await as synchronization. If you're following more of the functional model, which actually can help you avoid data races, then you do a get of the tile inside the async await, in which case you'd get the communication also.
Yeah, I think unless you're doing...
It's, if you, yeah, a runtime person would think of it as it's a single assignment variable. Yeah. Yeah, I mean, the data-driven future is, and the backing data, it's up to the programmer as to, we did not want to dictate a functional programming model. A functional programming model would say everything is copy semantics, which you can certainly do, but we didn't want to require that. If you can just use it for synchronization and access shared state on your own. So for example, in our Degas project, we are looking at the global address space. We would just use this for synchronization, and then the body of the async could have PGAS access.
Yeah, talk to the PGAS.
Yeah.
Okay.
Okay, thank you.